Hey guys, Mr. Jantzen here. In this video we're going to cover ways 11 through 20 on how to pass the Regents exam. So here we go. Here's number 11. It says the true shape of the Earth is called an oblate spheroid. Once again, the Earth isn't a perfect sphere. It's slightly bulgy at the equator and slightly flattened at the poles. Okay, now this is very slight, all right? But because the Earth is spinning, this rotation causes this slight bulge at the equator. So the equator is actually a little further away from the center of the Earth than the poles are. Okay? If you were going to see this as a practice question on the Regents, the best evidence that the Earth has a spherical shape would be provided by what? Now this is a little tricky because it says a spherical shape, not a perfect sphere. So the best evidence that we know the Earth is round, okay, are pictures. Okay, pictures taken from space, or choice B. Okay. Cool. Let's go on to number 12. It says the best model of the Earth at any reasonable scale is a perfect circle. Look, yes, it is slightly bulgy and it is slightly flattened at the poles, but it's so close to a perfect circle. When we calculate the roundness ratio, it's like 0.997 round, okay? So if you were to pick a model of the Earth, you'd pick the one closest to a perfect circle. Students have a little trouble with this because they hear bulge and they're going to pick an object that has a slight bulge to it. But no, it's so close to a perfect circle, you want to pick the one closest to a perfect circle. Okay, if you're going to see this as a Regents question, you know, this is a classic question: which diagram most accurately shows the cross-sectional shape of the Earth? A lot of students are going to pick choice D, but that would be incorrect. Okay, you want the one closest to a perfect sphere, and that would actually be choice B. Okay, because it's so close to a perfect sphere. Okay, number 13. Oh, one of my favorites. The altitude of Polaris is equal to your latitude. Okay. Once again, the angle, or how high Polaris is in the sky, is equal to whatever latitude you're standing at. Okay, that's because Polaris is the polar star. Once again, it is directly above the North Pole. So when you're standing at the North Pole at 90 degrees north, okay, as shown here, Polaris is right above you. If you're standing at the equator, it's at your horizon. So whatever your latitude is, that's the altitude of Polaris. Okay. Which statement about Polaris is best illustrated by the diagrams below? So it's showing Polaris at the different angles, and this is kind of what the reminder was, that Polaris's altitude is equal to a location's latitude. Okay, number 14. Latitude lines are drawn east to west and measure angular distance north or south. So once again, you're going up the ladder or you're going down the ladder. Okay, latitude is flatitude. These lines run east to west and then measured how far north or south of the equator you are. Okay, students have a little trouble with latitude and longitude, but once again, if you just spend a little time, understand that it's almost like climbing a ladder or going down a ladder. The little rungs of a ladder represent the lines of latitude. How are latitude and longitude lines drawn on a globe of the Earth? So latitude lines are kind of parallel, they never intersect. Longitude lines and meridians, they do intersect. So the one that indicates that is going to be choice C. Latitude lines are parallel and longitude lines meet at the poles. Okay. Longitude lines are drawn north to south and measure angular distance east or west. So once again, these are meridians that converge at the poles. The main one is called the prime meridian right here, and if you're going to the right of the prime meridian, you're going east. If you're going to the left of the prime meridian, you're going west. Okay, so these are meridians that converge at the poles. All right. Okay, so the diagram below represents part of Earth's latitude-longitude system. What is the latitude-longitude of point L? Okay, well, we'd have to go up the ladder or down the ladder. We'd see that the L is below the equator, so that's south. Then we're going to the left or to the right of the prime meridian, and when we go to the left, we're going to see that it is to west, or 30 degrees west. So we have 5 degrees south, 30 degrees west longitude. Okay, longitude is based on observations of the sun. Okay, that's what our time is based upon, solar time. So once again, you know, the Earth rotate at 15 degrees every hour, so the sun's going to appear to go across the sky at 15 degrees per hour. All right, so longitude is what our time is based on. Okay, if you can see, this is a Regents question. It says cities located on the same meridian must have the same what? And it turns out they're going to have the same solar time because they're on the same meridian. Okay. Number 17, the Earth rotates from west to east 24 hours. So one rotation is 1 day. Okay, it's going to appear to rotate from a west to east from the North Pole. And, you know, once again, that causes day and night. Right. As a Regents question, it says the basis for time difference between adjoining time zones is Earth's what? Okay, So once again, we know the Earth spins, but it's a question of how fast it spins. It spins 15 degrees every hour, or choice 4. Okay, number 18. Earth revolves counterclockwise when viewed above the North Pole. So once again, most things in earth science, believe it or not, are counterclockwise. High pressure systems are not. They actually rotate clockwise, but you know, pretty much everything else kind of goes counterclockwise, if that helps. So once again, it takes 365 and a quarter days to go around the sun one time. Okay, 1 year is 1 revolution. All right. Once again, that extra quarter accounts for leap year. Every 4 years, you add a quarter and a quarter and a quarter and a quarter, and you add an extra day on in February. That's why it's there. Okay, so 1 revolution, as indicated by your reference table, is 365 and a quarter days here. Okay, if you were to see this as a Regents question, all right, you would see that it says which event is a direct result of Earth's revolution. Okay, evidence for revolution, okay, is going to be the fact that you see different constellations different times of the year. When the Earth is on one side of the sun, you can't see the constellations on the opposite side. So the fact that you have different constellations, different times of the season, is evidence for revolution. Okay, cool. Number 19. The sun appears to rise in the east and set in the west. Once again, the keyword here is appears. The sun's not doing the movement, we're the ones doing the movement. We're the ones rotating. So as we spin, what's going to happen is the sun's going to appear to rise in the east and set in the west. But we're spinning at 15 degrees per hour. So if we're spinning at 15 degrees per hour, then it's going to make the sun look like it's going across the sky 15 degrees per hour. Once again, this is an observer. He has the sun directly overhead at noon. So just a little extension here. This is probably at the equator on the equinox for this observer because it's directly overhead as noon and it's rising due east and set due west. A Regents question is going to say, to an observer, the sun will appear to move from, well, it's kind of what I just said. Once again, it's rising in the east and setting in the west, and it's going to be at a rate of 15 degrees per hour, or choice A. Number 20, the moon has phases because the angle between the Earth and the moon changes because the moon revolves around us, okay, and it always is half lit. Okay, so once again, the moon revolves around the Earth, okay, and it's going to experiencing different phases depending upon the angle at which we view it from Earth. Okay, right now it's full moon phase, then it's going to come around here to the last quarter phase, then once again it's going to come into the new moon phase. As you view it from the Earth, it looks like there's nothing lit up. Okay, so it's the angle at which you view the moon from Earth is going to cause your phases. Okay, just kind of a nice summary diagram right down here. Whenever you get a diagram like this, just make sure you understand where the sun is. Sometimes they put the sun on this side of the diagram, sometimes on this side of the diagram. But you know that's going to be key when you kind of answer a Regents question. So let's take a look at a Regents question and check it out. So the question states, a cycle of moon phases can be seen from Earth because why? The moon's axis is tilted, the moon spins on its axis, the moon revolves around Earth, or the moon's distance from the Earth changes at a predictable rate. Once again, the revolution of the moon around the Earth is going to cause the phases, or choice 4. Okay, so that is 11 through 20 in the illustrated ways to pass the Regents exam. Thank you for watching, and stay tuned for our next video.